In this video, we're going to graph rational functions. Recall that a rational function is a fractional function in which both the numerator and denominator are polynomials. So here's a couple examples of what a rational function might look like when we graph it. This first one here actually looks like a line. However, we have a hole at a certain point, at the point value of x equals -2. Now, where did that hole come from? If we take the original polynomial that we're given and we factor it out, we'll see something interesting happen. So we take our f of x, we factor our numerator x squared minus 4 into x plus 2 and x minus 2 because it's a difference of squares, and we see that we have a common factor in both the numerator and denominator. We have an x plus 2 in both. So if we cancel those out, we end up with x minus 2. And in fact, that's what this graph is here. It's the graph of x minus 2. However, the common factor of x plus 2 in both has to be taken into account because our original problem still has an undefined value when the denominator goes to 0, in this case at x equals -2. So even though at every other point it forms this nice perfect line, there is one point in which we have a hole, and that point comes at the place where the denominator is equal to 0. Let's take a look at this other function here. A little bit crazier behavior. It's going across and then starts dropping down very rapidly at x equals -2, and on the other side coming from positive infinity until it evens back out. This function, we don't have anything in the numerator. It's in its simplest form, 1 over x plus 2. So whenever you have something in the denominator that doesn't cancel with the numerator, you're going to end up with a vertical asymptote at that value of x. Now you'll see this line also has a horizontal asymptote. And by that we mean that as you go in each direction, in this particular direction here to the left, the line gets closer and closer to the y equals 0 horizontal line, but it never quite touches it. And on the same thing going the other direction. It's closer and closer to that y equals 0 line, but never touches it. We're not going to focus on the horizontal asymptotes, but it is something to be aware of. So let's review those definitions. A hole, or point of discontinuity, occurs in the graph when there's a common factor in top and bottom. The hole occurs at whatever x-coordinate causes that common factor to be 0. Now going back here, remember that common factor went to 0 when we had x equal to -2. A vertical asymptote, the vertical line that the graph gets very close to but never touches, occurs when the function is written in simplest form and the denominator goes to 0. The function is undefined. So let's take a look at what that looks like again. Here, when the denominator went to 0, when x is equal to -2, and the function was in its simplest form right from the start, there's nothing you can do to factor this and simplify it. We had a vertical asymptote that approached the x equals -2 line. And finally, a horizontal asymptote is the horizontal line that your graph may cross. In this case, see how it did cross it, but it gets very close to it as it approaches different directions. So there is a way to jump that line. In most cases it will not, however. Again, we're not going to focus on that in here. But the gold line is the horizontal asymptote, the purple line is the vertical asymptote. So from each of these functions, let's determine if there's any vertical asymptotes or any holes. First thing you need to do in problems like this is completely factor both your numerator and your denominator so you can see if there's anything that's going to cancel out. So let's go ahead and do that. In the top we have a difference of squares, so x squared minus 4 is x minus 2 and x plus 2. Denominator we have just unfoiling to x plus 3 and x plus 2. We see a common factor in the numerator and the denominator that we need to take into account. So that will be a hole. And then we see another area where we're going to have the denominator go to 0, but it doesn't cancel out with something in the numerator, and that's going to cause a vertical asymptote. So let's take a look at that. We have the common factor of x plus 2, and therefore we have a hole at the place where that goes to 0, x minus 2. On the other side here, we have that x plus 3 term. Excuse me, I'll simplify the function after we cross those out. I'm going to actually cross those out right here. So now we're in our simplified form, this x minus 2 over x plus 3, which we can also see right here. And now we get to our vertical asymptote. That's going to occur at x equals negative 3 because that's when this highlighted area, the denominator in its most simplified form, goes to 0. So that's our vertical asymptote. Let's repeat the process on this side. Again, in our numerator, we have a difference of squares. So that is going to factor into x plus 3 and x minus 3. And in our denominator, we're going to have, we're just simply unfoiling, and we'll get x plus 5 and x plus 3 as our two factors. So the first step is to completely factor that original polynomial in the numerator and in the denominator. Once you do that, you look for things in common. In this case, we have a common factor of x plus 3. Once we have our common factor, we know that we can identify a hole at that area. And that hole is going to occur when that common factor goes to 0. So in this case, the hole is at x equals negative 3. Now let's simplify our function completely by crossing out anything that is in the numerator and denominator. So get rid of that x plus 3 term, and we're going to be left with x minus 3 over x plus 5. Now always remember to report that hole at x equals negative 3. Finally, we'll use this function here to determine where our vertical asymptote is. It's going to pop up in both of these places here. And our vertical asymptote is going to be at x equals negative 5, because that's when the denominator of the function in simplest form goes to 0. So the final answer with problems like these is you report where your hole occurs, then you simplify the problem as much as possible, and report where your vertical asymptotes occur, always by looking at the denominator.